In this video, I'll talk about descriptive statistics that are things we can calculate that describe the data that we're seeing. So the first main descriptive statistic that we use a lot is the mean or the average. Now what I have here is a formula. It's a mathematical formula. It looks scary. It has like all kinds of symbols, but I wanted to include the formulas here because I think it's important that you actually learn, that you understand something like this, what it means. What is this? That you can make sense of it and derive from this what you have to do, how you have to calculate something, or how you have to implement it in software. Of course, in JS, there's just a button that you press to get the mean. For all these things, actually, we don't actually have to calculate any of this stuff by hand, but it is important that you understand the basic idea behind it. So on the exam, for sure, there will be a few questions where you have to compute or calculate some things like the mean or standard deviation or correlation by hand as well. It's important that you understand the concept. So what's happening here? Well, let's take it one step at a time. First, we have x with a bar on top. So x here stands for the variable. Could be like happiness or loneliness or anything. And maybe instead of x, we use like h or l or y or really any letter. It doesn't really matter. We place a bar on top. This is the bar. We refer to the sample mean. The sample mean means the average score in the sample. Okay? So the average level. Then here we see x again, but now x doesn't have a bar, it has a subscript I. I is like a lower, right? Lower, that's why we call the subscript. What does that mean? This means the observed score for person I. Now who's person I? Well, person I could be anyone. Could be 1, could be 2, could be 3, could be 4. Right? So for example, we have a data set like this. Let's say with some measures. Let's say 5, 2, 1, 3, 4 different people. Right? And x I is this one if I is 1. This one if I equals 2. This one if I equals 3. And this one if I equals 4. Okay, so xi, x subscript I, is a different variable, right? Related to number 5, number 2, the number 1, and number 3, depending on the level of I. And that's where this notation here comes into play. So let's look at that. We have this big symbol here, which is a capital letter sigma. In statistics, we love Greek letters. But we love them because we have so much stuff to define, we run out of letters, so we use a whole different alphabet to get more letters. Right? Sometimes they even use other alphabets as well, but I usually stick to the Roman and the Greek alphabets. So this big capital letter sigma means sum all values to the right of the symbol. So we have the symbol here, everything to the right of it, and sometimes you actually see the notation where you have brackets to indicate what you're actually summing. If you don't have it, literally everything to the right of it is being summed over all values of I. So those are these subscripts below and superscripts above. I equals 1 and n. What this refers to is we start at I equals 1 and we end when I equals n. N is the number of people in our dataset. So for each of these values, I equals 1 or 2 or 3 or 4 or 5, take this and then sum all those values together. That's what this notation is telling us. Right, so if we go back to our data here, we start with I is 1, then we go to I is 2, then we go to I is 3, then we go to I is 4. We don't do anything, we just list them, and then we sum them all together. Just adding them, all right? Then we finally have this notation here. Well, n here is the sample size, the number of people. 1 over n is 1 over that number. So multiplying by 1 over n is the same as dividing by that number. Right, so what this literally says is the mean equals the sum of scores divided by the number of scores. That's what it says. 1 over n is dividing by the numbers, multiplying with this, and this is the sum. Right, and that's the first formula that we saw in this course. We're going to see A few more, of course, but this is the first formula that you saw. And this is the proper notation. Like I could write it simpler. I could not do the subscript, for example, right? Like I did before, to say mean equals sum divided by number. But this is the way that you would write this properly. Like it has all the notation in there. There's like the bar here, there's a multiplication. This is a multiplication symbol, right? So it's the same as multiplying, but we don't like to write the cross symbol because we already use x a lot. So that's why we write the dot symbol, multiplication. So 1 over n multiplied by the sum. All right, we can also think of this as an algorithm. So here, we get the same formula. And basically, we first take all the data, right? All the data here, scores. We add them, we sum them all. Then we multiply 1 over n or divide by n, and then we get our mean. So this is what you do when you calculate it yourself. You just take all these data points, you add them, and you multiply by 1 over n, and you get the mean, right? Relatively straightforward calculation. Okay, so let's have a data set here. So now we have example data. Here I measured some animals on their happiness and loneliness. Obviously, this is made up data. It's not real, right? I tried to ask a hamster, how happy are you? But the hamster said beep, beep, beep. And then I tried to ask a penguin, but the penguin just walked away and swam. So I made up data instead, right? So this is just completely made up. So we have scores of happiness, we have scores of loneliness. Okay, so now how do we compute the mean? Well, to do that, x bar, the mean of some variable, x will be h or l, happiness or loneliness. We have 10 observations, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 observations. So we're going to multiply by 1 over 10. And then we have the scores of all these subjects. So let's see the mean of happiness. Now I write h bar, the mean of happiness, equals 1 over 10 times, right, times, and then the sum. Adding all these numbers together, 15. And for loneliness, the sum is 14, right? Now, can we say that people on average are more happy than they're lonely? No, that doesn't really make sense, right? We don't know the interpretation of the scale. Could be that loneliness is measured on some sort of different level, right? But what we could do is see, okay, is for example, maybe this is one group and this is another group. Can we compare those on the means of these scores? And that's something we're going to do, of course, in this course with, for example, t-test or NOVA. So the mean gives us the average or the center of the distribution. Basically, we have 0 to 30, right? And this is 15. We know that for happiness, the distribution should be centered around here. But what about the spread? How big is this distribution? For that, we calculate the standard deviation. The standard deviation or the variance. But now calculate the standard deviation, which is S. So the standard deviation. Right, that's a really scary formula. So let's take it one step at a time as well. What's happening here? So as the standard deviation is also the average distance from the mean. So that means that if I have a data set, let's say my mean is 15 and the standard deviation is 5, I can interpret that as saying, okay, on average, people were 5 points away from the mean. So how do we calculate this? Well, the first thing we look at is the deviance, the deviation. So this is the actual deviation from the mean. We have the score, and now we subtract the mean, okay? So let's say we have a score of 20 versus a mean of 15, then the deviance is 5, right? 20 points higher. And we want to get an average distance, right? So the average deviance, really, from the mean. Okay. Now, problem is that the mean will be the center points of all these deviances. So if we sum all these deviances and we don't do anything else, we just sum this, we are going to get 0 on average. Why? That's by definition of the mean, because the mean should be in the middle of all these points. So we can't get the average deviance like that. We need to do something else. What are we doing? We are squaring it. Squaring means multiplying something by itself. Let's say 5 squared equals 5 times 5 equals, now I have to think, 25. The nice thing about squaring is that the number is always above 0. Or equal to 0 if you're squaring 0 itself, of course. It's never a negative number. So we don't have this problem that we get some values above, some values below the mean, and that the average is going to be 0. The average of this is going to be something non-zero, and we can interpret it. So we have the square deviance, which is this one, a positive a measure of how far away is something from the mean, and it's always positive. All right, then we take some of those. We take a sum of that, like we did in the mean as well. Then we get something we call the sum of squared errors. And actually we're going to define this, like we have some versions of this. We're going to talk about this much more later in this course as well. For now, we just call it the sum of squared errors. And now we want to take an average. So again, we divide by n, but now we divide by n minus 1. What? Why are we dividing by n minus 1, not by n? That's weird, right? Because other than that, it's just an average of this, and then the square root symbol in the end, that's just basically the square root is counteracting the square, right? So x squared, square root of that is x. So we put it on squared units, and now we're putting it back in normal units, so to get like it on the same level again, like I had before. So that's why that big square root is there. But we're dividing by n minus 1 and not by n. That's really, really weird. The reason for that is because we are including here an average that's also based on the sample. So there's also information in here. And actually some information on the deviance is lost by including that mean. Simply put, if you only have one observation, like say we have happiness for one guy, like let's draw a fish. I can only draw a fish. There we go. 2 eyes, happy fish. Very happy guy, has 28. Oh. On a 30-point scale, scores 28 happiness. Really, 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 really happy. Okay. And we have only one. Then the average is 28. Now, can we say something about how much deviation we have from this average? No. Because we have only one data point, and h minus h mean equals 0. Squared also equals 0. So we're going to get a sum of squares of 0. But yeah, that's just because it's based on one value. But maybe the true happiness in my sample is actually something else. And we miss out on that information because we have to use this estimate. Right? That's why we're losing 1. I'll talk more about this later. For now, just remember that you have to divide by n minus 1 because we are using a sample here. Okay? And that's the standard deviation and how you calculate it. Again, we can think of this in terms of an algorithm. We have all our data points. For each data point, we take out the mean, we get the deviation, we square it, we get a square deviations. And those are the things we sum. And then we multiply by n, 1 over n minus 1, or divide by n minus 1. We take a square root because we squared here, so we're counteracting that. Then we're back to units that are interpretable, which is the standard deviation, or S, as we call it. Now that thing is pretty useful and pretty important because it tells us something about how much participants differ on the scores. So let's look at that. How do we compute the standard deviation? Right, so oh wow, that's a lot of numbers on the slides, but don't be scared. It's just doing the same thing over and over again. We first calculate the sums of squares. So for each of these values, we take out the mean. Right, so we have 28 minus 15. And then we have 0. Oh, that's a really sad parrot. That's sad. Okay. 0 minus 15. Etc, etc, etc. And we square those values. So we have something that's non-zero. If you do not square them, then the sums of square, well, this is not, wouldn't be sums of squares because you're not squaring it, but the sum would be 0. We get something 1054. Now actually, we can't really, this number is hard to interpret on the scale, but the rest we're doing is just kind of standardizing it to some interpretable scale. When we're looking at the variance in the data, we just look at this number. This is a thing that will go into the F value, for example, which we'll talk about later. Okay, then we calculate the standard deviation. So we have to do 1/9, right? Because we lost one piece of information basically including the mean, times this sum square and square root it. You get 10.8. So we expect an average score of 15 with an average deviation of 10.8 around this average, which means that, okay, sure, right? Our sample had like an average score of 15, but there's quite a lot of spread around that. On average, people are 10 points away from that, even though they could be a maximum 15 points away from it, because it scales from 0 to 30. That's quite a lot. Okay, so now verify yourself at home. Well, you're at home now, maybe watching this, so pause the video and check that the standard deviation of loneliness is 8.5. If not, then yeah, message me, tell me, hey, that's not correct, it should be something different. You try to calculate this yourself. In the exam, you'll also have to calculate something like this yourself, and I expect that you can do this. All right, so now let's talk about Z values or Z transformations. So a Z transformation is a way that we can transform a variable into a bit more of an interpretable scale. And all we do is we take, I should have actually included a subscript here. We take the response of someone, we take out its mean, and we divide it by the standard deviation. Then we get this Z value. So this means we can interpret the Z score as being Z standard deviation from the mean. If I have a Z score of 1, it means I'm 1 standard deviation above the mean. And that makes it really interpretable. Especially if we can assume a normal distribution. Because if we can assume a normal distribution, when we know the Z scores, we already know quite a lot. So the normal distribution, the standard normal distribution has a mean of 0 and a standard deviation of 1, which is basically what you always get when you get Z scores. It always has a mean of 0, standard deviation of 1. In the standard normal, we know all these probabilities pretty well. We know, for example, that the area around the mean with 1 from -1 to +1 Z, which means the area between the mean with a -1 standard deviation and the mean +1 standard deviation, is about 70-ish%. Actually more like 68, right? About 70-ish%. We also know that if you look at 2 standard deviations from the mean, the area between that is about, not exactly equal, but about 95%. 95%. So that means that most participants will fall in this range between -2 and +2 Z. So if you get a Z score of, let's say, 3, it's a really strong outlying case, or like, yeah, someone that's not very far away from the average.